friends, welcome to School is Cool. Today we are going to see different number systems used and the way to convert them to each other. We use different number systems to perform several functions. So, what are the types of number systems and what are the differences between them? There are four main number systems, namely decimal, binary, octal and hexadecimal. The difference between these number systems is the base used. What is the base of a number system? It is simply the number of digits a system uses. Like, decimal number system has the base 10, binary number system has the base 2, octal number system has the base 8, while the hexadecimal number system has the base 16. So, let's dive deeper and understand about each number system. The decimal number system is the most commonly used number system. The number system we all use, from basic arithmetic to complex calculus. As the name suggests, it has 10 digits. Deci means 10. So base 10. It has the digits 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So now time for a small fun fact for you. Why do we use a number system with base 10? The reason is that we have 10 fingers, right? So man started his early calculations on his fingers. So there is a need to have a distinct number for each finger, right? That's how decimal number system came into existence. Fascinating. Binary number system is the next. It has the base 2, meaning it has 2 digits, namely 0 and 1. It is mainly used for handling and operating computers. Computer works on electricity, so it understands only two states, presence of electricity, that is 1, and absence of electricity, that is 0. You might have seen in movies that when a computer gets hacked, a series of zeros and ones pop out. That code is nothing but binary code on which the computer works. The next is our octal system. It has 8 digits, 0, 1, 2, 3, 4, 5, 6 and 7. You will wonder why we use the octal system. I mean, we understand that we have 10 fingers, so decimal number system is used. The computer understands only 2 states, so binary number system is used. But why 8 digits? Let's see. There are 2 major reasons behind this. The first is to represent binary numbers in a more compact way. We know that 2 cubed equals 8. So 3 binary digits are equal to 1 octal digit. So it gives a compact representation. That's why we use octal system. Second reason is that a byte consists of 8 bits. So with base 8, we can directly perform calculations on bytes. This is like 2 birds with 1 stone. The next number system is the hexadecimal number system, which has the base 16. You will wonder how 16 digits can be represented. We have only 10 different digits to represent. So, does the hexadecimal number system have different digits? The answer is yes and no. That means we use alphanumeric system. We have 10 numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. And then we have 6 letters A, B, C, D, E and F. This makes 16 digits in total. One example of this number system being used is the representation of colors. Like, you must have seen some painting application which asks you to choose color from a standard palette or to enter the hexadecimal code of that color. The RGB code to represent black color is 000000 and for white color is FFFFF. Now that we have understood that computer uses only 0 and 1, then why don't we see these codes while using our computers? The reason is that the computer converts our inputs. For example, in a calculator program, we give our numbers to the computer in decimal system. The computer then converts those numbers and instructions into binary code, processes them in binary, and then again converts the binary code to decimal numbers, and then gives us the output in decimal system. So how exactly does this conversion happen? Let's see how numbers in different number systems are converted into one another. So, today we'll see different types of conversions. So, our first is decimal to binary conversion. So, let's take an example of 94 to the base 10. We write the base as like this in the subscript. So, we'll convert this into binary. There is a very easy method for that. So, we make 4 columns that are dividend, divisor, quotient and remainder. So, we'll write 94 as the dividend, as it is our number. Then in the divisor, we'll always write 2 because binary has the base 2. So, we'll continuously divide it by 2. And we can get the remainder only as 0 and 1 as the divisor is 2. So, binary has 0 and 1. Thus, we use 2. So, we divide it by 2. Write the quotient, that is 47, and write the remainder 0 over here. Then we again divide 47 by 2 and get the answer as 23 and remainder 1. Then we divide 23 by 2, get the answer as 11, remainder 1. 11 divided by 2, we get the answer as 5, remainder 1. 5 divided by 2, quotient 2, remainder 1. 2 divided by 2 is 1, remainder 0. But we will not stop here when we get the quotient 1. We will end till we get the quotient as 0. So, we will again divide 1 divided by 2, quotient 0, remainder 1. Then, our next and most important step is to write this in this order. So, our binary number would be 1, 0, 1, 1, 1, 1, 0 to the base 2 as it is binary. So, we can say that 94 to the base 10 is equal to 1, 0, 1, 1, 1, 1, 0 to the base 2. Now, we'll move towards our next conversion. Our next conversion is binary to decimal conversion. So, let's take a random number like 10, 11, 0, 1, 0 to the base 2. Now, I have seen very different methods. Some are very difficult while some are easy. So, I have a very easy method over here. So, what we do is space this out and then we draw a L shape like this for each number. Then what we do is write these numbers here. 0, 1, 0, 1, 1, 0, 1. Now, what we have to do is multiply each with the powers of 2. So, the first digit should be multiplied with 2 power 0. The second one will be multiplied with 2 power 1. The third with 2 power 2. Fourth with 2 power 3. Fifth with 2 power 4. Sixth with 2 power 5. And seventh with 2 power 6. And now we get the answers. So 0 into 2 power 0. 2 power, any number power 0 is 1. So 0 into 1 is 0. 1 into 2 power 1, that is 2 power 1 is 2. So 1 into 2 is 2. 0 into 2 power 2, 0 is there. So we directly write 0. 1 into 2 power 3, 2 power 3 is 8. So 1 into 8 is 8. 1 into 2 power 4. So that is 16. 0 into 2 power 5 is 0. And 1 into 2 power 6 is 64. Then we add all these. So we write 2 plus 8 is 10 plus 6, 16, 20. We carry over 3 and 6, that is 9. So we get the answer as 90. So we can say that 1011010 to the base 2 is equal to 90 to the base 10. Now we'll move towards our next conversion. Our next conversion is decimal to octal. So let's take an example like 198 to the base 10. So like binary, we have the same method for octal. So we again write dividend, divisor, quotient and remainder. So now octal has the base 8. So we'll divide it by 8. The divisor will be always 8 over here. So we'll take 198. Divisor is 8. So we get the quotient as 2 and 4. 24. And our remainder will be 6. Like this we will do again. So 24 divided by 8. We got the quotient as 3. Remainder is 0. 3 divided by 8. Quotient 0. Remainder 3. So here too we have to divide till we get the quotient as 0. So we get again like binary, we write in this form. So we get 306 to the base 8. Now we'll move towards our next conversion. Our next conversion is octal to decimal conversion. Let's take an example of 763 to the base 8. We don't say it as 763, but we say it as 763 as it has the base 8. Now, again like binary, we'll space this out and then draw an L from each of the numbers. So we write these numbers over here. Then we multiply with 8 power 0, 8 power 1 and 8 power 2. So 8 power 0 is 1. So 3 into 1 is 3. 6 into 8 power 1. 8 power 1 is 8. So we get the answer as 48. Then 7 into 8 power 2. So 8 power 2 is 64. So 7 into 64. We'll do that. 64 into 7. 4 sevens are 28. 2 carry over. 6 sevens are 42. 42 plus 2 is 44. So we get the answer as 448. Then we again add these. So 3 plus 8 is equal to 11 plus 8 is 19. We carry over 1. 4 plus 1 is 5. 5 plus 4 is 9. And then we have 4 over here. So 763 to the base 8 is equal to 499 to the base 10. It was easy, right? We'll move towards our next conversion. Our next conversion is decimal to hexadecimal. So we'll take an example like 345 to the base 10. Like binary and octal, hexadecimal has the same. So we'll write dividend, divisor, quotient and remainder. So our dividend is 345. Our divisor will be 16 over here, as hexadecimal has the base 16. Then if we divide 345 with 16, we get the answer as 21 and remainder as 9. Then we take 21 over here, divided by 16, get the quotient as 1 and remainder as 5. We will not stop here and end until we get the quotient as 0. So 1 divided by 16, quotient 0, remainder 1. Here we get the answer as 159. Again, we don't say it as 159. We say it as 159 as it is hexadecimal. So 159 to the base 16. So 345 to the base 10 is equal to 159 to the base 16. We'll move towards our next conversion. Our next conversion is hexadecimal to decimal conversion. Let's take an example of A80F to the base 16. So again, like octal and binary, we'll space this out and then draw else. So here f has a numerical value. Of course, we cannot operate on letters, right? So for that, we have a table. In that, the values are A is 10, B is 11, C is 12, D is 13, E is 14 and F is 15. So, F is 15 as we know. So, we write 15. 0 as it is, 8 as it is, and A is 10. So, we write 10. Into, again write octal and binary, 16 power 0 into 16 power 1 into 16 power 2 into 16 power 3. So 16 power 0 is 1, 15 ones are 15. 16 power 1 is 16, but there is a 0, so we write 0. 8 into 16 power 2 is equal to, so to find out, what we'll do is multiply. So 16 power 2 is 256 as we know. So we take 256 and then multiply it with 8. So 6 8s are 48, 4 carry over, 5 8s are 40, 44, 4 carry over, 2 8s are 16, 16 plus 4 is 20. So 2048. We write it over here. Then our next is 16 power 3. We don't know 16 power 3. So we'll take 16 power 2, that is 256, and then multiply it with 16. So we'll calculate this and get the answer as 4096. You might wonder how I got this answer so fast. So I used a trick for it. You can watch the video Cool Math Tricks 3 to improve your speed in multiplication. So here we got the answer as 4096. Then we multiply it with 10. So we get 40960. We'll now add these all. So 5 plus 8 is equal to 13 plus 0 is 13. And carried over. plus 4 is 6, plus 6 is 12. 1 carry over here. Then 1 plus 9 is 10, 0, 1 carry over. 3 plus 0 is 3 and 4 as it is. So we get the answer as 43023. So A80F to the base 16 is equal to 43023 to the base 10. Friends, it's fun time. Time for a small puzzle. The question is, prove that Halloween is equal to Christmas. Think over it. If you need more time, you can pause the video. I hope you have thought over it. So, as we know that Halloween comes on October 31st and Christmas comes on 25th. So, October 31st. If we write it like this, I think this is looking like octal 31. So, let's find out. We have learned how to convert octal numbers into decimal. Let's refresh our memory. So, 31. Again the same. 1 into 8 power 0. 3 into 8 power 1. So, 1 into 1 is 1. And 8 power 1 is 28. So 3 into 8 is 24. When we add it, we get 25. So we get decimal 25. Oh, this looks like December 25th to me. Yes. So October 31st and December 25th are the same. It was interesting learning about some fun facts and conversion of one number system to another, right? So, if you are new on my channel, subscribe to my channel. Also, don't forget to like and share this video. We will meet in another video with many another cool tricks and tips. Goodbye till then.